Hello, in this video we're going to solve exponential equations for the first time, and we're going to use a method of creating the same base. This is not how we're going to solve most exponential equations, but this will be how we start off the process of solving exponential equations. Later on we're going to use the inverse function to solve an exponential equation, which is a logarithm. But right now we're going to use this fact. If we can create the same base on either side of the equation, then if the bases are the same, then the exponents have to be the same. So for example, if we had 5 to the x equals 5 to the negative 6, then that must mean that this exponent right here is the same as that exponent because the bases are the same. If the bases are the same, that means x has to equal negative 6, and that is our solution for that equation. Now, if we have a function where we don't have the bases being the same, we have to create the same bases by looking at this factor and saying, okay, can I reduce this into another factor? Well, 3 to the x is the lowest factor I can use there, but 81 has some factors of 3 in them. So we could rewrite this problem as 3 to the negative x is equal to 3 to the 4th power, because 3 to the 4th power is 81. Once you figured that out, you can put that in there. Now we have the bases are the same, so that means the exponents have to be the same. So negative x has to equal 4, then that means x is equal to negative 4. So that's the solution to this one. All right, moving on to the next example. This one's a little bit trickier because it doesn't have a whole number. So we have to use what we know before. In a previous one we talked about this, or I talked about this, where these are reciprocals of the regular powers. So in reality this is a power of negative 1. So 5 to the negative 1 power is 1/5. Okay, it's a reciprocal of this raised to that power, which is to the first power. So 5 to the negative second is 5 to the second, which is 25, and then the reciprocal, which is 1/25. So it's the same thing, but we're going to take the reciprocal of that number. So in this case, I'd rewrite it as 5 to the x plus 3 equals 5 to the negative 1, and then I would solve the exponents, and I'd say x plus 3 equals negative 1, and then I'd subtract, and I get negative 4 as my answer. X is negative 4. Same answer as the second example. All right, now sometimes we can't write one in terms of the other, so we have to reduce both of the bases. So this one was base 5. These are not going to reduce. This 27, I can't go 9 to some power equals 27. That's not going to work out. 9 to some power is not equal to 27. There is a power that works here, but it's fractional. So we probably wouldn't use that. So what we would do is we try to reduce these to the same power. We want to notice that 3 to the second is 9, and 3 to the third is 27. So now we have a common base here. So I'd rewrite this as 3 to the second, all raised to that power of negative x plus 15. And then this one is 3 to the third, all raised to the power of x. Now when we raise powers to powers, that means we multiply them. So in this case we multiply these powers, so this exponent equals this exponent, so my equation becomes 2 times negative x plus 15 equals 3x. And that's what we're going to solve to get the solution. So we have negative 2x plus 30 equals 3x. Move the 2x over, so we have 5x equals 30. X is 6 in this problem. And we could try that out on our calculator. Let's just make sure that it works. So on the calculator, just to verify, so if I put 6 in there, that's going to be negative 6 plus 15, that's 9, so that's 9. Oops, we have to turn it back on. 9 to the 9th power. So that's what we get for 9 to the 9th power, and then that should be the same as 27 to the x power, which is 6. So let's make sure these two are the same numbers, and we can verify they are exactly the same numbers. Therefore, we did solve this correctly. All right, and the final example is with the base of e. Now remember, e is about 2.718. E is about 2.718. But that's not necessary. We have the same basis. So that means that we can just equate the exponent. So that means 3x is equal to 2 minus x. So we move this over, we get 4x equals 2. X is 2 over 4, which is 1/2. So that's my solution for this. And we could test that out on our calculator. So that one would be e to the 3/2 equals e to the 2 minus 1/2, which is still e to the 3/2. So this is going to equal 3/2. So that should be the same because the exponents are the same, bases are the same. Well, I didn't need my calculator there. All right, so remember e is this base, about. So it's like pi, it's an infinite decimal, and we just don't write that infinite decimal out. We write a symbol for it as e. It's growing a little more than, it's more than doubling. It's a little more than doubling, but not quite tripling in the time amount. That's what e is doing. All right, so this is the final thing in chapter, or in this week's work. If you have any questions on this, shoot me an email, and we'll see you for the upcoming test in the next couple days.